Okay, I just wanted to give you guys a little bit of a tutorial about using Phase 2 software from Rock Science. It's a finite element based stress analysis software that you can use extensively in geomechanics problems like slope stability and especially for underground excavations, which is the topic of our course. So I know we had a tutorial about a month ago on this, but I wanted to give you this video refresher. So here we go. This is the main dialog, main window for the model building portion of the software. And you can see that there's a lot of menu commands where you have these drop-down menus to access all the important commands that you'll need. And there's also icons to represent most, if not all of them. And you can see that some of them are grayed out. And they're grayed out when they're not available due to the options you selected or because of whatever phase in the model building process you're at. So for starters, we're going to set up our model by setting these project settings here. So the general settings, we use a plane strain analysis, and we're going to use the metric units in MPa. The stages is the number of stages that you're going to try to simulate. For instance, we're going to simulate, in this case, a state before mining has occurred with no excavation. And then we're going to have a second stage where a tunnel has been excavated. And you can have quite a number of stages. I'm not sure what the limit is, but a lot. And you could, for instance, a stage could represent adding a load to a boundary or excavating another tunnel, or perhaps you're going to excavate a stope in multiple sub-stages. So I'm going to use 2 stages in this case. And the rest of it, the analyses settings, project settings will stay the same. Project setting, you can put a title in for your project. And you can put your company and so on. And a number of other comments. Okay, so the first step is to build your model geometry, and you have to include all the geometry that you're going to include, the interior and exterior. So I'm going to make the interior tunnel boundary for starters. So I go up to add an excavation. And then you can see down in the bottom right, there's an area where you can enter information. So you can either click a bunch of vertexes for an excavation. I'm going to hit Control Z to undo that. Or you can enter them down below if you want to put more explicit locations. I think I'm going to go with a circular excavation. So I'm going to use I and push enter, and then a little dialog comes up. And I'm going to select a center and a radius. And I'm going to want my tunnel, in this case, to have a radius of 2 meters. Meters is the default unit. And I'm going to use 40 segments. So the tunnel's going to, well, actually that's a bit much. Maybe 24 segments. Segment is a small linear section that makes up the circle. And I'm going to center this at 0, 0. So just to show you Another trick, so I go down to the bottom right. You can see that there's a flashing icon down there. And I'm just going to enter 0, space, 0, enter. And there's my tunnel with 24 segments with a radius of 2 meters. I'm going to go up here in the zoom controls, and I'm going to zoom all. See the tunnel. Okay. So now I'm going to zoom back. The next thing I'm going to do is I'm going to add the external boundary of the model. External boundary defines the full extent of the modeling region. You want to have the model extents far enough away from your excavation that you're not going to have boundary effects. In other words, the boundary is not going to change your answer based on how far away it is. A good rule of thumb is that you want your boundary to be 5 to 10 tunnel diameters away from the tunnel. Okay. So I'm going to go here and I'm going to add an external boundary, and it's going to give me the option of automatically selecting a box type boundary around my circular tunnel, and it's going to use an expansion factor, which is kind of a multiple of the radius, and I'm going to use, say, 7. Okay, so you can see that we're about 7 diameters away from the tunnel. And so in that way, the tunnel boundary, which is an artificial boundary, it represents an artificial truncation of the true geomechanical extents. In other words, the rock really goes on forever, but we're going to truncate it so that we only have to simulate a minimum area necessary to get an accurate solution without having to have so many zones and such a large model that it takes forever to solve. Okay, so now we have an external boundary and an internal boundary, and this is a good time to add any internal boundary conditions, like for instance, say I want to have 2 materials, so I could add a material boundary. Say there's an overburden up here, and then I right click and click done. So I can break these into 2 materials. Say for instance I wanted to excavate the tunnel in 2 stages. Then I could put a stage boundary. Clicking on the vertexes here, and there's 2 stages, and then I right click and click done. You can also add a joint. So there's some other information that you need to select about the numerical representation of a joint. You can look in the user's manual to figure out how that works. But for now, I'm just going to keep it at the default. And I'm going to say that a joint passes at an angle below the tunnel. And right click and done. If you wanted to move a vertex around somewhere, you can go up here and you can move vertex, and then click on the ones that you want. Click done, say you've selected all the vertexes that you want to move. Then click on it again and move it wherever you want. Okay. You could also add a vertex. If you wanted to put some more complexity into your geometry, oops, that's the move button. I meant to hit the add vertex button. And then you can see that red cross there, and bang, we added the vertex. And then done, you can either hit right click and done, or you can even just hit escape. on your keyboard. And then you could move that vertex around if you wanted to make more complex geometry. Okay, right? Lots of options. Now, because we want to excavate this in 2 stages, the tunnel, we actually need to add another stage to the model setup. We'll have 1 stage of initial in situ conditions, and 1 stage when we excavate the heading of the tunnel, and a 3rd stage where we excavate the bench in the bottom. Okay, so we go up to here to project settings, stages, and we'll just add another stage. You can even add names to them to keep it clear. Okay. Now let's zoom the extents of this thing. And we got quite a bit of information in there, so I think it's probably a good time to save this thing. So let's save it on the desktop as tutorial phase 2. Okay, so we've got the geometry established very nicely. The next thing we're going to want to do is mesh the model. Now, meshing basically discretizes or breaks up the entire model region into small zones, in this case triangular zones, where all the calculations take place. So the more zones you have, the more intensive the calculation is going to be and the longer it's going to take. However, the less zones that you have, or the coarser the mesh, the less accurate your model will be. So designing a mesh is all about compromising. You want to have the most refined mesh that you can get without being excessive and leading to excessive calculation times. And you also want to make sure that the mesh is finest or most refined in the areas of the model that you are most interested in. And typically, those are regions where there's high stress gradients or high stress changes. Around a tunnel, the stress gradient is highest in the near field of the tunnel, where the stresses are going to be perturbed. So you want to have a lot of refinement here. Out near the boundary, the stresses should be fairly uniform and more like the in situ stresses, so they can be much coarser. If you had a problem where you were going to apply a foundation load, for example, to the top of the model, then that's another area where you might want to have some refined mesh. So the mesh is developed in 2 stages. First, you discretize the boundaries, break it into intervals. And then Phase 2 software has an automated algorithm that develops a triangular mesh on the basis of those discretized points. So we go up here and we can click discretize. And you can see it has broken it up into some fairly fine discretized spacing along all of these elements. And from there you can simply push the mesh button and it will automatically generate a mesh. To be honest, it looks pretty darn good right out of the box. That's pretty fine. Around the tunnel it's fine. It's fairly coarse as it moves away from the tunnel. I'm pretty much satisfied with it right out of the box. But, you know, say you wanted something coarser or finer, you can do all kinds of things to manually control how the automatic meshing will develop. So we can delete all this, okay, and start over. Now over here, you can see a little drop-down menu where you have Mesh Setup. And in there you can adjust all kinds of settings. You know, how the grade, whether it's a graded or a uniform mesh. Graded means it changes size from one discretized boundary to the other. Uniform means it would be in whatever region you applied it to, you'd have zones is pretty much all the same size. And that comes in handy sometimes. And you also have a gradation factor if, say, you didn't want it to grade so severely, or maybe you wanted to grade or change size as it moves away from the boundary even more dramatically. And here we got the default number of nodes on all excavations. So that's the when you hit discretize, the number of nodes that will basically appear along each element. So for instance, why don't we reduce that to say 60, and let's discretize it again, and then mesh it. It made a very slight difference. If you really wanted to, you know, really control it even more carefully in certain regions, you could have applied, say, stage boundaries internally here. And then you could have explicitly controlled the discretization and made it even more refined. So there's a lot of things you can do with meshing, but I think this is a pretty good mesh for our problem right out of the box. Now you'll notice that when I meshed it, it automatically added some boundary conditions. These triangles we call fixed boundary conditions. So for instance, the top right node is fixed. That means it's fully fixed from moving in both the X and the Y direction. So all these boundary elements are fully fixed from moving in the X and the Y direction. There's another type of boundary called a roller boundary that we can use. Let's get rid of all these boundaries here by clicking Free Restraints, and then we'll select everything. And maybe we'll say Done. Okay. So say there's two types of roller boundaries. So an X restraint only. We'll click on all of these three segments and push Enter. So roller boundaries means it cannot move in the X direction, but it is free to move vertically. Okay. Now, what that simulates is a plane of symmetry. So it's like this entire model, in terms of stress analysis and deformation, it's like this entire model is reflected over here. And that's how it's going to respond. And that symmetry can be used to your advantage in some cases. For instance, if the model is truly symmetrical, you could simulate half of the tunnel. In this case, the model setup is not truly symmetrical because you can see, at least not symmetrical along the middle of the tunnel, that the definition of these material boundaries is not symmetrical on both sides, and the presence of this joint is not symmetrical on both sides. Okay, so we have to model, in this case, the entire tunnel element. So the boundary conditions are pretty far away from this tunnel, so I think either fully fixed or roller boundaries would be suitable. And I'm just going to go back to using fixed in X and Y. And I'm going to select all the external boundary. elements. Okay. I think this is probably a good time to save everything. So we have the tunnel geometry, including all the geometrical representation of the geology, the tunnel boundary, even a stage boundary for the excavations. And I think now it might be time to add some material properties. Earlier I said that this would be an overburden, but that really wouldn't make sense with these boundary conditions. In this case, because it's fixed everywhere, this is not representative of simulating the free ground surface, which would not be fixed for movement. Obviously, the ground surface is a free surface. So let's just say this is another rock material, and this whole simulation is deep down in the ground. Okay, so let's add material properties way over here to the left. So we could call this shale for one rock type. And we are going to use isotropic elasticity, meaning its stiffness is the same in every direction. And let's use 10 GPa. Remember, this is in MPa, so 10,000 MPa. We'll use a Poisson's ratio of 0.25. We have a more Coulomb model selected with some default parameters, strength parameters, to define the more Coulomb failure envelope. But we're just going to leave it as an elastic material. So really, none of these strength parameters or strength criteria comes into effect anyway. So we can just leave it as is. Let's go to material 2, and we'll call this one sandstone. And we'll make this one strength of 10 GPa and 0.22 for the Poisson's ratio. And we'll also leave this elastic. Okay. So we've defined the characteristics or parameters for two materials. Now let's apply them to the model. So this little assign properties dialog is what we want to use. A little dialog window comes out. We just select shale for starters, and then we just click in the region that we want to assign as shale. It didn't do anything because the shale is actually the same color, this default color already, because it's the first material. So that's already shale. Now we'll click on sandstone, and we'll start clicking in this region and the bottom region and the interior of the tunnel is all a sandstone. Okay. So now we've assigned material properties and everything. Now the last step, first we should save here. The last step is to assign the in situ stresses. So we can click on this stress cube here, and we can say we are going to assume that this tunnel is deep down in the ground with no ground surface having any effect. These boundaries are artificial, just carving out a section of the rock to look at. And we're going to say it's deep enough that the gradient of stress from gravity loading, due to the unit weight times the depth, is not really a factor because the in situ stresses, tectonic stresses, are so much greater. So let's use a constant stress field, and we'll say that sigma 1 is 15 MPa, and we'll say sigma 3 is 5 MPa. So that's a K of 3. And we'll say that sigma z, which is the stress out of plane, and it matters in the failure envelope, so it has to be a reasonable value, or ideally the correct value that's measured in the field. But we'll say that in this case it's 9 MPa, somewhere intermediate between sigma 1 and sigma 3. And next we have to tell it the angle that sigma 1 acts in degrees from horizontal, and the angle is degrees counterclockwise from the positive x-axis. So if we want to say that sigma 1 is vertical, we put 90 degrees in there. Okay? And you can see from the stress block that the maximum principal stress is in the vertical direction, and it's 15 MPa. Okay? So that is the stress field acting inside of the model extents. Okay, let's save it again. So at this point, the entire model is all set up, at least for our stage 1, the in situ conditions. So this stage 1 will represent the pre-mining stage before we mine out this tunnel. Okay, so although you can see that the tunnel's geometry is there, we haven't excavated. It's as if it isn't there. It's full of rock. You can clearly see. But what we want to do now is go down to the bottom left, and we want to click on Excavate Heading. And then we click on that Assign Properties box again, and we click Excavate. Then we can just select the tunnel heading, click on it, and it'll be mined out. Then we go to Excavate Bench stage number 3, and we can still having excavate selected, we can select the bench, and then that is mined out. So then at this stage the tunnel will be fully mined. Okay, so that takes the model through the in situ conditions, the heading excavation, and the bench excavation. Everything is all ready to go. So we'll save it one last time, and then we should be able to run the model. So we will select Compute, and the computation engine will open up, and it will solve the finite element problem with these boundary conditions and these material properties and stress conditions, and should give us a solution. So then we go up to the Interpret dialog, and we can see the results. Okay. So first off, let's have a look at the vertical stresses. You can see this drop-down dialog will allow us to look at the stresses in the model, and the contours are shown in this legend over here to the left. So let's see sigma YY, the stresses in the vertical direction. And you can see that although there's a lot of color changes, that basically it's more or less saying it's 15 MPa everywhere. Although clearly there's something going on with this joint, and that's because of the boundary effects from the end conditions that we decided to use for this joint, and they're obviously having some small minor effect. But we can see the important part is that the vertical stresses are 15 MPa, and that's what we wanted them to be. That's what we entered, and you always check to make sure that the model has executed and provided the results that are exactly consistent with the way that you set them up. Okay, so let's look at the X stresses. And again, they're about 5 MPa with some kind of perturbation near the boundary. And it's important to note that, so the boundary, like I said, is far away from the tunnel. So ideally, these stress changes here are not going to have any effect really on the stress. Stress is calculated around that tunnel. And then we look at sigma z to make sure that that's correct. And we get about 9 MPa. So it looks like we've set the model up very well and everything is behaving properly. So let's go back to sigma 1. And from there we can look at the excavation response by changing the stage. And let's zoom in on the tunnel area. So we can see we've got some high stresses developing over here on the spring line, which is very consistent with a high vertical stress, up to 38 MPa or so. Very high. That's about twice of the in situ stress level that we entered, and that seems reasonable. And they're very low in the roof of the tunnel, in fact possibly even tensile, which is also consistent with this kind of stress regime. And then let's look at the bench. Okay, we've taken out the bench, and it just looks like a butterfly pattern that looks exactly like you see in most textbooks. High stresses of 38, 30, 32, 34 MPa in the spring wall, in the spring line, sidewall area, and low stresses in the roof and floor. And you can see that this joint had a very minor effect. Now this is all an elastic model, so there's no yielding in the rock or in the joint, so there's no real significant stress redistribution, well, no stress redistribution from yielding. And so it's more or less a textbook answer. And you can look at many other things here. You can click on vectors of deformation to see what direction the rock is deforming around the tunnel, and of course this is all highly exaggerated, and you can go into the display options to change the settings. You can also click on deformed boundaries, so that's a greatly exaggerated view of the deformation of the boundaries, including the joint. And if you've done an elastoplastic model, then you would have the option to display yielded elements. It'll look something like this, only it'll have some red lines in it, and that'll show you where the model is predicting any yielding, where the rock, where the stresses have exceeded the strength of the rock. Finally, here's another nice one: is stress trajectories. So you can see from this how the stresses are flowing around the opening. So the long axis is the direction of sigma 1, the short axis is the direction of sigma 3. So in the far field, like over here on the right, you can see that it agrees very much with the stress block that define the in situ stresses that we used. And around the tunnel, you can see how they flow around the tunnel boundary and create stress concentrations, and in the roof and floor where they're greatly reduced from some kind of shadow effect, maybe from the tunnel boundary. So there's also many other ways you can query output data. For instance, up here, add material query. First, let me turn off these contours. I'll add a material query, which allows me to draw a line or a point anywhere to get output information. Say I want to draw a line here at the spring line, and right-click and done. And it says, gives me different options for how many spaces I want to get information from along that line. I'm going to say at 10 locations. And there I have the stresses sigma 1, which is what I have set up here to view, plotted at discrete points. If I want different information, I can change this drop down to whatever I want, and the query will also change accordingly. And from there, I can right-click and I can graph it, and I can even copy the data and put it into Excel. So let's see what a graph looks like. This is a plot of distance along that query line versus sigma 1. Very nice, very helpful. So I think that sums up the basics of using Phase 2 to carry out analysis, especially for underground excavations. There's many other tips and tricks and subtleties and advantages of using different techniques, and a lot of it is explained in the manual for Phase 2. And I encourage you to look through that and maybe try one or two of the tutorials there to increase your skills, because using this kind of modeling is a tremendous skill as an engineer. It allows you to really experiment and carry out effective and efficient design.